Hi everyone, so this is Miss Polly and I will continue with the second part of this chapter, our chapter 11, which is direct current. Now on this second part of this lecture, we'll be focusing on these three main topics. The first one is to understanding EMF or electromotive forces, and also internal resistance. And after that we will see what will change when the resistor was connected in series and parallels. Last but not least, which is the main topic or the main heart of this chapter, which is a method to calculate the value of V, I and R in a complex circuit, which known as Kirchhoff law. Now bear in mind that Kirchhoff law is an alternative method to calculate V, I and R. The original equations to find V, I and R is actually from Ohm's law itself. Now we continue with our tutorials. So what is EMF? Now EMF is a device that use a chemical, mechanical or other energy to provide the potential difference. This is the key point, the potential difference necessary for electric current. So any type of sources or device that based on chemical, mechanical or other energy that can provide a potential energy to a circuit and produce an electric current is we call as a source of EMF. Right, so EMF is actually a shortened form electromotive forces. We usually using EMF to make it simple, and the closest example of EMF or source of EMF is actually batteries and cell. You have this in your handphone, in your laptop or in any of your electrical appliances that what is it that on or function using an electric current is actually from electromotive forces. So in these chapters or in this point, we will see two types of EMF sources, which is batteries and cell. So cell and batteries come in all shapes. You know all about this one. They all have their own voltage mark on the side. I think you realize that when you bought some battery from any store, you will see 12 volt, 14 volt or 6 volt. That was actually their own voltage. Now this voltage is actually what we call as an EMF of the battery or cells. So as once again, EMF is stand for electromotive forces. Now let's say I connected a voltmeter to the terminal of a cell. The number that shows in your voltmeter is actually a measurement of the EMF. So let's say I have a battery with the value of 1.5 voltage here, connected it with the voltmeter. The reading I will observe from my voltmeter is supposed to be equal to 1.52. Right. The EMF also tells you how many joule of energy the battery will supply to every coulomb of charge which passes through it, because 1 volt is also equal with the 1 joule per coulomb. So that was EMF. So this is a few more points to understand what is EMF. EMF is a source EMF of a source is a work done per unit charge. We can also say that the EMF value in any source of circuit is the work done per unit charge. A source of EMF or EMF of source is also a potential different across the terminal of the source in open circuit, and it is also potential different across its terminal when it's not connected to circuit, which is closed circuit. And also is the electrical energy that generated by a source so that the charge can flow from one terminal to another terminal of the source through any resistor. So the SI unit of voltmeter, the SI unit of EMF is equal to volt because it is a potential energy. So it is symbolized as a V, capital letter of V. So this is EMF. Now, another word that I need you to understand is internal resistance. So what is internal resistance? Internal resistance, let's say in a cell or battery, the negative ions are attracted by anode and the positive ions are attracted by the cathode. We all know about this. So the flow of this ion will produce a current, of course, right? Because your ion will move from one point to another point with the energy, and it's supposed to be produce current. However, the collisions between the ions and the recombinations of opposite ion will reduce the flow of the current. So for let's say I have a few ions in one space or in one container. So I need I make the ion move from one point to another point. So there is a possibility that the ion will collide between each other or recombine between the opposite ion. Then this phenomenon or these two factor will produce or will reduce the flow of the current, right? So this resistance, this is what we call as a resistance. Actually, the recombinations of the opposite ion and also the collision between the ion is what we call a resistance in the cell. Now this kind of resistance is actually what we call as internal resistance, right? Now internal resistance can be symbolized as an R, but with the small letters of R. It is similar. The definitions is quite similar with the resistance of the resistor, but this is owned by any electrical appliances or electrical instrument, not only in resistor, right? So for let's say over here we have our resistor and we also have our battery. Now in my for the resistor itself, the functions of resistor is actually to resist the movement of the ions, which will reduce the flow of the current. So we have our R over here. So this R over here is symbolized as this R. So this is the symbol of resistor. Now we also have our battery over here, which is our source of EMF. This is the symbol of the source of the EMF. And let's say this battery over here was drawn in a symbol of this space, this yellow space, this yellow rectangle, right? So we know that the EMF itself is equal to this one because this is because this is actually the functions of the battery which produce the source of EMF. Now in this rectangle of battery, it also contains what we call as internal resistance. So we will have our R, small r over here, which is stand for our internal resistance. So in this full circuit of ours right now, we will have two type of resistance. One come from the resistor itself, and then another one come from our battery, which is our internal resistance. So when we close this circuit, we actually have two value of resistance. Hence the total resistance in this circuit is equal to this one, which is R, the biggest the capital letters of R with the small letters of R. So I hope you understand what is the definitions of internal resistance. For let's say this battery over here was replaced with another electrical appliances such as, or electrical instruments such as inductor. Then inductor itself also have their own resistor, with which we call as a internal resistor. Also, if we add another instrument over here, let's say a capacitor, so capacitor itself also have their own internal resistor. So that was internal resistor. I hope you can get what is the definitions of internal resistance. Right. So from that analogy right now, which is our battery over here and also our resistance over here, then we actually will produce what we call a potential difference in this point and in this point, which the relations, suppose by logic, the V that pass through or come from this battery will pass through to this resistance with a similar value. Let's say I have 12 volt produced from this battery. Suppose this 12 volt will be used by the resistor, pass through this resistor from point C to point D with the similar value, which is 12 voltage. Alright, so how to prove this value is actually from these derivations. So I have my EMF over here, which this EMF, we use the formula of V equal to IR, our Ohm's law. So I substitute the V with the E here because our epsilon is stand for the EMF of the source. I here, since there is no other junction that need to separate the I, so I have only one value of I here. So I only have one value of I here, times with the R, since in this closed circuit of mine right now have two type of R, which is our R, small r and bigger R from our resistor and our internal resistance. Then we have two value of R over here. Now expand these equations and I will get another expressions of this equation with this one. Now I know that the product of I here with the value of resistance, which is at this point actually, is the value of the voltage that passed through point C to point D, which will bring me to this value right now. So by rearranging this one, I will get a value or expressions of voltage that pass through this resistance, which is equal to this one. This is just a rearrangement. Then I know that this one, which is our epsilon minus with the current that pass through over battery with the ratio value of the internal resistance, is actually the voltage that pass through between my point A to point B. Hence I will get a new expression, which is this one. So we also know that VAB is equal to VB minus with the VA due to this one. And R over here, which our bigger capital letter of R is a external resistance, which is owned by the resistor itself, and the small r is our internal resistor, which is owned by our battery. So this is actually the expressions of these or the expressions of the relations between the internal resistance and also the resistance from the resistor itself. Now we continue with our resistors here. I know some of you is familiar with the words of resistor, so but then I want to once again introduce to you what is resistor. On last chapter, or on previous chapter, you did learn about a capacitor. So there are three basic instrument in circuit that you need to know at this level. First is capacitor, which you already met through chapter 10. The second one is resistor, which you will see it more in here. And another one is inductor, which will introduce to you in our last chapter, chapter 14, accelerating current. So you have these three basic electrical instrument in basic circuit that you need to understand with each other. Now bear in mind that at the end of the chapter 14, you will have to combine these three things, and we will see what happened to the I, V, and R when these three combine to each other. So what is resistor? So resistor is a device used in electrical circuit to maintain a constant relations between current flow and voltage. I think you know what is resistor actually. Even the name of the instrument itself is come from resistance, which is resist. So the function of resistor is actually used to lower the voltage at the different points in a circuit. Okay, now resistor work as they turn voltage energy into heat. So that's how the voltage was different, or they lower the voltage at different point in circuit. So this is the symbol of the resistor that we usually use in a circuit, and there is two functions of. Now, so this is some of the symbol for resistors. Some you might have see it everywhere, some you might not very familiar, but then in this level of yours we will use this symbol, which is by NEMA system, and this is the real life shape and picture of resistors. This is in a computer or laptop board, and this is in a singular board. Now right, so resistor can be connected into two ways, in series and also in parallel. So in series, the connection supposed to be just like this one, where the resistor, let's say I have three resistor, R1, R2, and R3. These three resistor was connected and rearranged in a series positions, and then connected to the power source, which is in this case is our battery. So for resistors in series, the current, which is I, flow through each resistor supposed to be same. So when the I was out from this battery, our power source, our electromotive source, the same value of I will pass through this R1, R2, R3 and back to the battery. Hence I can write the relations of I from the power source that pass through in 1, 2 and 3 is equal to this formula, which is I is equal to I1 equal to I2 and equal to I3. Now that was for current, but then for the voltage it will be quite difference. So for the voltage or total potential difference for resistor in series, the equation or the relation supposed to be written just like this one. So the total difference from the battery is supposed to be equal to the voltage in resistor 1, voltage in resistor 2 and voltage in resistor 3. Similar with the resistor resistance itself, the equivalent resistance supposed to be the total of resistance for the 3 resistor in your circuit. While for parallel, the sketching for resistors in parallel supposed to be just like this picture, where R1, R2 and R3 will be connected in parallel. If you don't know the difference between parallel and series, for the parallel you will observe a junction over here. So when the current I from power supply was out and flow, and some of the current will be flow into the resistance 1 and some of it will go straight. And then this current that goes straight will be again divided into two value of current, which is the other part will be go to resistance 2 and then the other one will go to straight to resistor 3. So if I want to write the equation for I over here, it will not be similar with the resistor in series anymore, because the expressions of current in this type of circuit will be just like this one, where I is equal to I1, where it is passed through the resistor, the first resistor, plus with the I2 and plus with the I3. So this is the total of the I, which is come from our power supply. While for the voltage in each resistor will be similar. So let's say I have a power supply with value of 12 volt. That 12 volt will similar in resistor 1, resistor 2 and resistor 3. Hence the expressions of voltage for the total and also in each resistor will be just like this one. And as for the equivalent of resistance, it will be by applying the Ohm's law, you will get these expressions of the equivalent resistance. So if I need to find the equivalent resistance, then I have to use this equation. So this is the equations of the equivalent resistance in a parallel circuit of resistor. Now this is the next part of this chapter, which is also a very important part that you need to pay more attentions. Now I will in this long period of lecture video, I will only sum up and explain to you the concept of this law. I will separate all the example on how to apply this law to do your tutorials in another video. So please, after you finish with this video of lecture, continue with the video of example that I provided to you. So this is Kirchhoff law. So what is Kirchhoff law? Kirchhoff law is, as I said earlier of this video, Kirchhoff law is actually a method or a procedure to calculate the value of I the value of V, and the value of R. This tree was actually originally can be calculated directly by using Ohm's law, which is V is equal to IR. So for, let's say I want to find V, then I was given the value of I and I know the value of R, just times these two things, the product of it supposed to be the value of V. Or if I need to find the value of I, just bring the value of R into the other side, then I will get the value of I. So how about a quite complex circuit? Then in that case we can't use this formula anymore. Instead, we will use what we call as a Kirchhoff law. So Kirchhoff law is actually a method or alternative, one of the alternative to calculate these three things in a complex circuit. There are other methods than Kirchhoff law, such as potential method and etc. But then in this level of yours, I will only teach you the Kirchhoff law. So there are two statements, or there are two facts that you should know in Kirchhoff law. First, Kirchhoff law is divided into two law. One, we call it as the Kirchhoff first law, or also known as the junction law, or also known as the current law. Now, what did this law say? That it states that the algebraic sum of the current at any junction of a circuit is supposed to be equal to 0. Once again, the sum of the current at any junctions of a circuit supposed to be is equal to 0. Now I can express this word into a form of equation, which is these equations. So I can express it into this expression, which is the sum of I is equal to 0, or the sum of I that into the junction is also the sum of I that out from the junction. Now let's see this picture over here. Let's say I have a circuit where there is a lot of junction in it. So for example, in this case, I have this I over here, this wire over here, and then this wire was divided into two junctions. One was over here and one was over here. So let's say the I that come to this junction was called I1. So it is into the junction. Then the other two will be out from the junction, which the denotions will be different with the I1. So this is I2 and the other one supposed to be in I3. Now when I write this expression in a form that follow this statement, it will be supposed to just like this one. So where the total of I into the junction, which in this case there is only one current that direct towards the junction, which is I1. So I1 is equal to the total of I that out from the junction. So in this case right now, there are two current that out from the junction, which is my I2 and then my I3. So the total of this one will be this one. So as follow this expression, as follow this law right now, I will get an expression for this junction, which is I1 equal to the total of I2 plus with I3. Now for, let's say I'm having another junction over here. So for, let's say I have junction just like this one. So the power source is from this one. So the current from that power source was direct to this point. Then for, let's say I have another EMF over here. So this this current from this EMF also towards the junctions over here. So at this point, both of these will be combined together and divide into two junctions. Remember, to follow this law, there's supposed to be a current that into the junction, and there's supposed to be the current out from the junction. Then you will follow these rules. If there is no out of current, but then there is a current that into the junction, then you will not follow this law. So as for this one, for let's say this is I1 and then this I2, this is I3 and this is I4. When I write this one by following the rules of Kirchhoff's law, I will have I1 plus with I2 equal to I3 plus with I4 due to the rules of this one. Now for let's say the value of there is only one EMF in this circuit, then my I1 is supposed to be out from that junction. So this I2 right now, sorry, I2 is out from the junction. So this I2 right now was belong to the I of the out. So this is the first law of Kirchhoff. Right, that was the first law, and then this is another important law of the Kirchhoff, which is second law, or also known as loop law or voltage law. Now, what did this law state? It stated that the algebraic sum of the voltage across all of the element of any closed loop is equal to 0. So once again, the algebraic sum of the voltage across all the elements of any closed loop is 0. Or this law also can be written as this one. Instead that in any closed loop, the algebraic sum of the e.m.f is equal to the algebraic sum of the product of the current and resistance. Now, what is the difference between these two? Now, for the first statement, let's say in one circuit I have three battery. So I have three battery. So by using this law, the total of the V in this circuit right now was actually will become V plus V1 plus V2 plus V3, which is equal to V equivalent. Now this is the meaning of the first statement. Now how about in a circuit I have one resistor and then combined with one battery, and then I connect it again with one resistor. So I have R1 over here, R2 over here, and I have my EMF over here. So how to find the algebraic sum of EMF in these cases? Now, as I said in the topics of internal resistance, there is internal resistance in this part, and there is resistance in this part, and also of this part, obviously. Now, when this loop or this circuit is in closed circuit, the current will flow through the resistor and come back to the EMF. So each of these resistor was actually have their own V due to V equal to IR. So how to find V in each of the respective resistor? I need to know what is the value of I that pass through to this particular resistor times with the value of resistance itself, and I will get the value of V. So for let's say this is V1, and similar with the one that passed through with on R2, so V2 is also a product of I that passed through to this part, which I need to know, times with the R2. So this just now is equal to V1 equal to I times with the R1. And the total of the V for these three things in this particular circuit is equal to EMF plus with the I times with the R2 plus with the I times with the R1 due to the value of this and also the value of this one. So that's actually the meaning of the second statement. Now, in simple expressions, these two can also be written just like this one. So the total of EMF in a closed loop is also equal to the total of the product between I and R for each element in your circuit. And the total of potential difference in closed loop is supposed to be equal to 0. Now, before we continue with the example of Kirchhoff law, I need you to understand a few sign, because in Kirchhoff law, it is very important to you to determine whether the I is equal to negative form, or the resistance is in negative form, or the voltage is in negative form. So how to determine these directions, which is symbolized by the negative and positive, is by using this one. So let's say in a circuit, I'm the current, or sorry, it's not the current, the directions of your loop is from the positive value to negative value. The value of EMF in this battery is equal to negative directions or negative value. Now, once again, I need to emphasize this one to you. Let's say, the directions of my loop, the blue one is the directions of my loop. So what is these directions of loop? You will know in my example furthermore. Now, if the directions of the loop in my circuit decided to move from positive terminal to negative terminal, the value of EMF for this battery is negative sign. Can you get it? And vice versa. When the directions of loop was from the negative sign to positive sign, this one, the value of EMF supposed to be positive. Now imagine, this is similar with this analogy. Imagine you are from the peak of UMS hill. So this is the peak. From the peak of UMS hill, you need to go down from that peak. You're supposed to use a very low energy due to the gravitational directions, which is towards the earth, the center of the earth. So you will observe that you have a very you need a very small energy to go down, and it is very easily for you to go down from the highest peak of that UMS to the lowest peak. So when you just need a very small energy, then you have to release all the other extra energy in yourself, right? That's why there is a negative signs over here when the directions of the loop is from positive terminal to negative terminal, and vice versa. The analogy, when you need to hike the hill of UMS from the lowest peak to the highest peak, you need an extra energy, right? to reach that peak of UMS. So that extra energy, you need to add anything. Doesn't matter you drink 100 plus, or eat your chocolate, as long as you reach that peak. So the thing that you add for yourself to gain more energy is similar with this one. When the loop is moving from the lowest ground or lowest terminal to the highest terminal, which is positive, then I need to gain another energy. So the EMF is equal to positive. So that was the analogy of this first convention. And the second one is this one. Now please take note that the blue one is the directions of the loop. What is this loop? I will, and once again, I will show it to you through the example of this chapter. And the red directions over here is the directions of the current. Okay, can you get it? You can see that there is no directions of the current on the battery, right? Because obviously current in battery will move from negative to positive directions. In battery, I just need to look for the directions of the loop. But as for the resistor, this is the symbol of the resistor. As for the resistor, due to there is no terminal positive or negative in the resistor, so I have to consider two directions, which is the directions of the loop and the directions of the current. Now, once again, the blue one is for the loop and the red one is for the current. So let's say when I pass through this resistor, and the directions of the current, and the directions of the loop is similar with the directions of the current, the value of V for this resistance is equal to negative. And vice versa. When the directions of current is different with the directions of the loop, the sign of V in this resistor is positive. Now, this is the analogy. Let's say the current is U, and this is the wave of the oceans. So, when you swim at the sea, doesn't matter anyway, as long as there is a wave. So, when you swimming at the sea or any place with the wave, so this is the wave, the loop is the wave. When you swim with the similar directions of the wave, you don't have or you don't need an extra energy to move you from one point to another point, right? So what happened to your extra energy? You need to lose it. That's why there is a negative sign over here. But differently, when you move with the opposite directions of this wave in the ocean, you have another or extra energy to you be able move from one point to other point in the oceans. Hence, you need to gain more energy. That's why there is a positive there is a positive symbol over here for the V. So that was the analogy of this one. Now remember once again, when the directions of the current is similar with the directions of the loop, the value of V is negative, and vice versa. When the directions of current is opposite with the directions of loop, you will have a positive directions. This is just for resistor. Why do I need to consider both of the directions of the loop and current in resistor? Because resistor because there is no terminal for resistor. There is no positive terminal nor negative terminal in resistor. And once again, as for the cell battery, since it has terminal positive and negative for the battery, so I just need to consider the directions of the loop. So when the directions of the loop was from positive to negative terminal, the value of V is equal to negative, and when the directions of loop from negative terminal to positive terminal, the value of EMF is equal to positive. Okay, so that was the second law. Have you I hope I hope you are very clear with this one before you moving on with the example. So please don't get dizzy with the explanations of mine. Hopefully you can go through, or you can get more understanding through the example. So let's continue with the Kirchhoff law first. So what is the difference between, or what is the comparison between the two Kirchhoff law? So the first Kirchhoff law, as you see just now, it's called a junction rule due to the junction, and the second law is loop rule, or also voltage rule. The junction rule also called as current rules. So this is basically the comparison of both this law. The first one, junction rule, this law is applicable to both closed and open circuit. Meanwhile, as for the loop, it is applicable only for the closed circuit due to the value of V. Because when your circuit is in open condition, there is no current going through or flowing through your circuit. So you don't have, or you don't need any loop rule to apply on it. Junction rule in accordance with the law of conservations of charge, because conservation of charge said what I have for in will supposed to be you gain in out. So that's why the total of current when you come into the junction is also equal to the total of the current out from the junctions. Loop rules in accordance with the law of conservations of energy, because the total of energy for in is also equal to the total of energy of out. Last point for the comparison of both these rules is the algebraic sum of current at junction is equal to 0, as I show to you right now, and the algebraic sum of the potential drop in the closed loop is also equal to 0. So you can see the difference. In junction rule, I care about the current, the directions of the current, and also the total of the current in the whole circuit. While in the loop rule, I will only care or pay attention to the voltage. So if I have everything in my circuit, I have inductor, I have capacitor, resistor, then the total of the V that pass through each of that component should be equal to 0. So this is the comparison of the Kirchhoff law. Now I'm gonna stop here. I will have a different video for example on for each example of my Kirchhoff law. So please watch the video, and I will meet you at the video of example. Thank you.